Hello, everyone. I'm unable to attend the research meeting for the 29th of May, so I thought I'd record a video instead, but I'd be happy to present at a later meeting if Michael would like me to. My presentation today I've titled Towards Modular Universal Induction. This is a schema that I've been thinking about for a wee while now that I think might help describe a version of universal induction that's slightly different from Solomonoff induction Solomonoff induction proper, that might more closely resemble how large language models reason and indeed how humans reason. You should be able to see my slides there. This is my second take. I did a take almost all the way through that didn't have my slides. So just making extra double sure that they're there. Yeah. Great. So as I have observed before, Solomonoff induction as it was originally described, taking a Bayesian prior over inputs to a universal Turing machine, with the priors being defined by the Kolmogorov complexity on that machine, does define a upper bound for how well a reasoner can do, but it might not be a great or an ideal fit for describing how transformers reason. I think one reason for that is that Solomonoff induction is monolithic. That is, it considers separate hypotheses. It doesn't consider any commonalities between them. Any commonalities between them do get taken into account by the virtue of the fact that if there are two similar hypotheses that do well on the data, their predictions will get added together, and those predictions will probably be quite similar. But the Solomonoff inductor will not take any notice of that beyond noticing that the two hypotheses both give a relatively large posterior probability to the data that it has seen. By comparison, large language models, don't consider separate models of what might be going on. They build their model of the string that they're trying to predict by increasing in complexity. Lower neurons will activate on simple patterns like repetition or capital letters or numbers or things like that, and then neurons on a higher layer will combine those, and then on a higher layer will combine those, and they'll slowly build up these larger concepts into larger things like particular ways of programming particular functions, or formal language versus informal language, things that are hard to express simply but can be made up of smaller concepts. And humans seem to reason in a way that's not non-monolithic as well. We hold different models for different domains. My model of the economy is quite different from my model of the solar system, but both of them use my understanding of arithmetic, also of things like calculus and linear algebra. And we teach children things like arithmetic because it's useful in so many different domains. You can think of a million other domains, maybe not a million. You can think of a lot of other domains where arithmetic is useful, where you don't want to start from scratch and make a new monolithic model just for understanding some new domain. Obviously, that would be intractable. One scheme I proposed in a previous iteration of this meeting for an unbounded reasoning schema that would approach transformers better, I called unbounded transformers. That is, rather than trying every input to a universal Turing machine, try every assignment of parameters, and optionally also hyperparameters, to a particular transformer architecture. I think this matches more closely what machine learning engineers try to find the optimal assignment of weights to a neural network. I don't think it's a great match for modeling, how large language models reason, and it's also not a great match for human reasoning. It's only really a match for trying to find, a good assignment of weights to a transformer, obviously, which is more akin to finding a universal Turing machine than actually performing Solomonoff induction itself. So I think that Solomonoff's key insight was assigning priors based on Kolmogorov complexity, and that we can do that to many different things other than Turing machines. I've said before, Turing machines are not particularly special in the space of universal forms of computation. You can use anything else, right? Anything that is capable of universal computation. Turing machines are only special because they are relatively well studied and because they were described first. Which is why I can use assignments of weights to transformers instead. But what would it look like to adapt that so that we're not using monolithic models, but we're using different modules that can be reused between different hypotheses? Here's one way to do it that I came up with that I think can, on some strings, beat Solomonoff induction. In some ways, it might not make immediate sense how you can beat Solomonoff induction because it's an optimal unbounded algorithm, but it can be done in some ways with some asterisks. So if we take a infinite string that we're trying to predict, S, and a particular machine, U, usually I would say consider a particularly universal Turing machine, but in this case I would say it might be more fruitful to think of a particular universal programming language. I would just think of Python. That's probably the one most people in this meeting are familiar with. So we perform Solomonoff induction as before with machine U on string S. U will inevitably make some amount of total prediction error, which we can take the log to base 2 of to measure prediction error in bits. We can then consider all libraries, I've called them, L, with a description size of less than or equal to the total prediction error that U makes on S, E. Anything larger than that will cause, given as a prefix, will cause U to give a lower probability, but anything that is smaller has the possibility to encode within it regularities in the string that U has not fully updated on. We consider all those libraries as prefixes to potential programs on U. Then we perform Solomonoff induction again with every individual library that can serve as a prefix of size less than or equal to E. And if any library leads to less error than the machine without the library, we use that to predict the next symbols. And if there are multiple, which if there are any, there'll almost certainly be multiple, we use the one that uses the lowest error. In the limit, this will be equivalent to Solomonoff induction, but I believe that, at least in early stages, it might beat Solomonoff induction on some strings. I haven't demonstrated that, but I think it can be demonstrated. I don't think it resembles human or large language model reasoning very, very closely. It's probably closer to humans than large language models. Large language models don't really consider different, when they're given a string, they don't update their own, what their neurons do. They might, different neurons might activate on recognition of particular patterns, but humans might reason, more online. But it's still a little bit of a stretch. So I've put together some previous papers that I think might point the way towards a more modular, a better modular version of Solomonov induction. The first one is called Optimal Ordered Problem Solver, which has the acronym OOPS, which makes me laugh. Now, this is a provably near optimal. I'm not exactly sure what near optimal means. I think it's approaching optimal performance of solving a sequence of related problems that are ideally increasing in complexity over time. The example they gave was first creating a algorithm to recognize the language of n number of one character followed by n number of a second character, a times n and b times n, say. And then they gave it the task of solving the Towers of Hanoi problem. That is when you have three rods and different sizes of disks that need to be moved, and you can move a disk from any rod to any other one, but you can't put a larger disk on a smaller disk, and you have to move the whole pile from one rod to another. Which has the property that an optimal solution is akin to moving the entire pile minus the bottom disk to a rod, then moving the bottom one, then moving the other one again. So it's quite similar to the A times N, but B times N problem, because the solution will be evenly divided into two parts with one different intermediate step. Now, the way that it works is, after it solves a problem, it will take the solution that it found to that problem, freeze it as a reads-only module. It will be able to reuse it at any point. It will not be able to overwrite it or forget it. It will then split its time 50-50. I don't think there's anything particularly special about that ratio. It's just, the simplest way of dividing your time between two different ways of exploring solutions. 50-50 between exploring new solutions, trying to build solutions from the ground up, versus adapting old ones to the task at hand. That is provably near optimal as a way of, adapting old solutions to new ones, which is a potentially useful way of thinking about, obviously a Solomonov inductor doesn't solve a sequence of problems per se, but there is a way that you can think of, predicting the first 5 characters of a string as similar to predicting, the next 5 characters, or even just the next one. You might be able to think of that as a sequence of related problems instead of an ongoing problem of predicting the same string. So that's one piece of the puzzle. The second one out of 3 is from a paper called Universal Induction with Varying Sets of Combinators. Now, this is explicitly dealing with universal, aka Solomonov induction, defining a reference machine, which is sort of more just a form of computation for universal induction called combinatory logic. Don't worry too much about what that is if you're not immediately familiar with it. The point is that it's a kind of logic that is Turing complete, can form a universal form of computation. Now, they define it as starting with just two simple combinators, which is, they claim, sufficient for universality, which, in a sense is incredible, but also is, only as unbelievable as being able to produce a universal computer with only an AND gate and a NOT gate, which is possible. So they show that starting with those two combinators and then adapting the library of available combinators with combined ones, so that one that uses a combination of 5 different combinators, you treating that as a new primitive combinator, as it discovers more useful ones for the task at hand, solves some toy problems much, much faster than just using the original 2, which makes a lot of sense. It sort of slows down the combinatorial explosion of, just using 2 combinators for having to solve every single problem like that. It's like, again, going back to the logic gates, it's like combining an AND gate and a NOT gate to create OR gates and XOR gates and NAND gates and all the others. They explicitly say, though, that while adapting the library of available combinators is helpful in speeding up universal induction, which is very promising, they don't define how to optimally manage that library. That is part of where OOPS comes in, being a provably near optimal way of doing that. Now, I could just combine those 2, perhaps, but the thing about that is I don't want to just add a new solution every single character, because that just makes the universal Turing machine grow unboundedly. In a sense, the optimal way of defining modular universal induction is just to include every possible module as as being available to the universal machine. An infinitely large Python library, which would be fantastic in a sense. But that sort of just gets us back to plain old Solomonoff induction, in that every program is, rather than being a program itself, is just referencing part of the library. So we're just performing induction over parts of that library, which is infinite, instead of an infinite set of monolithic programs. It's not helpful. We need to be able to tell which modules are actually helpful in compressing the data, rather than just adding complexity to the universal Turing machine instead of 2 inputs to it. One way of looking at that is from a quite recent paper called A Complexity-Based Theory of Compositionality, which gives a formal definition of when a representation of some dataset compresses it and by how much. It's sort of just a relatively straightforward extension of Kolmogorov complexity, but conditional Kolmogorov complexity. So the amount of work that has to go into producing a particular data set versus the work that has to go into producing it given some representation of it. Now, they specifically analyze representations from deep neural networks, which is very, very handy that they have done the work of automatically analyzing neural networks, because it will also generalize to representations like modules in a universal inductor, which potentially gives a way of comparing them directly, which might let me demonstrate that transformers do it better than other neural networks, or possibly not, but gives me a good way of exploring that hypothesis, possibly. Putting it all together, I think it's possible to define an algorithm that uses combinatory logic as its reference machine, starting with 2 primitives, finds useful additional primitives, useful being defined by whether they decrease the Kolmogorov complexity of the string on the reference machine, and then using the optimal ordered problem solver algorithm, add in and freeze complexity reducing modules as the string is induced over. So I claimed before that I think this might be able to beat Solomonoff induction, which sort of doesn't make sense, because nothing can beat Solomonoff induction on every string, and nothing can beat Solomonov induction asymptotically. Solomonov induction will, in the limit, only make a bounded amount of error in bits, being equivalent, or rather being bounded by the Kolmogorov complexity of that string. But I think this could beat Solomonov A, by a constant number of bits, B, in the early stages of prediction especially, and C, on non-random strings, which is, I think, very, very important. As for how it's even possible to beat Solomonov, there are two ways I think that it's best to understand that. One is Solomonov's Pareto optimality. That is, Solomonov induction cannot be beaten on every string, but it can always be beaten on a particular string. Say, for a very simple example, the string consisting of just infinite zeros. Anything that assigns 100% probability to that string, which a relatively simple Turing machine can just output that string, will beat a Solomonov inductor, because the Solomonov inductor will always assign non-zero probability to every single possible continuation. Now, that string has a relatively low Kolmogorov complexity, so it won't make much prediction error on that string, but it will make some. It will always, always make some on every string. So it can always be beaten at least a little bit. This, the kind of modularity that we're talking about will be harmful on random strings. Any patterns that you recognize in the first n characters won't generalize beyond that. But it will be useful on interesting non-random strings, which I think are the only ones that we're actually interested in predicting. Secondly, it can possibly beat Solomonov induction by updating the choice of reference machine. I put universal Turing machine there, but of course, as I said before, it's more general than just Turing machines. Solomonov induction uses a static universal Turing machine with static priors defined by Kolmogorov complexity on that machine, but we might be able to cheat with this modular frame by changing what the universal Turing machine, how it encodes different programs as we go, adding useful, if we're using combinatory logic, adding different useful combinators to the reference machine so that useful programs have shorter description lengths. We're essentially changing our priors as we go and selecting not just better programs, better universal Turing machines, and then better programs on those better universal Turing machines. So not only will this, I think, be helpful in analyzing why large language models reason the way they do, and possibly why humans reason the way they do, but it might actually be a better universal form of induction than the one described by Solomonov. So my next steps on this, obviously I need to outline an explicit algorithm to do that, and investigate what those improved error bounds look like, and indeed if they are improved. Try it on some toy problems versus plain Solomonov induction and versus neural networks. See how much it beats either of them, or whether it beats either of them. See how complex a task needs to get before a modular reasoner pulls ahead of Solomonov. I think it would need to have some amount of regularity. So it would need to be at least a little bit complex before it can find commonalities between the parts of the strings that it's already seen. Then, as well as investigating the error bounds compared to Solomonov induction, compare its ability to compress those representations with neural network's ability to do that. That's the end of my slides. This is normally the part of the presentation where I say that I would like to discuss this and take any questions. Obviously, this is a video and I can't respond in real time. But if you do have any questions or comments, I'd love to hear them. You can send me a message on Slack. My Slack notifications have been unreliable recently, and I haven't been able to figure out why, but I promise I will check them tomorrow evening. Alternatively, you can send me an email. And yeah, other than that, I'll leave you to the rest of the meeting. Hope it goes well. Thank you very much. Bye.